In this particular practical, what we're going to do is have a look at simple harmonic motion again, and in particular, again, the phase relationship between displacement, velocity and acceleration, but also to observe the relationship between the period of oscillation and the mass. In other words, in what way does the time taken for one oscillation change if we have different masses on the mass carrier here? How are those two related? Now, the next thing we're going to have a look at is to directly measure that period and to work it out by using the mass and the spring constant. We looked at the spring constant earlier on. Again, what we're going to do is to compare the direct measurement of the spring constant as a ratio of the weight to extension with a value found in a different way. In other words, from the graph of t squared against m. So we're going to start off with a 50 gram mass, and I'll set this in motion. It doesn't have to be a very big motion, but I do have to make sure that it is going up and down like this and not wobbling from side to side. That's very important. So now I'll get the motion sensor doing its job.
Before we look at the results for the 50 gram oscillation, we need to record these numbers here for the mass, the force and the extension. We're not including the 0, 0 value for no mass and no extension. The other thing that we can do and need to do is to record the results for the calculation of the spring constant. Now, the spring constant can be calculated by dividing the force by the extension. So we can do that using a spreadsheet, and you can see the results here. So a formula was used to calculate the average, and you can see the formula up here. We can now have a look at the results from the timing of the oscillations for the 50 grams. The results for the 50 grams, what's happened here is that the three graphs have been arranged under each other. And if we have a look at the displacement, you can see up here that there is a position, it starts as at a position of maximum displacement. With the maximum displacement, we have a velocity of 0, and with an acceleration that is opposite in direction. It really means that these graphs are out of phase. And one of the questions in the book is the phase relationship between yt, that is displacement and time, and the velocity of time. Now that phase difference is a quarter of a period, or a quarter of a wavelength if you like, but we're going to write in a quarter of a period. The phase relationship between the displacement and the acceleration, if we compare this one with this one, it is half a period. So t divided by 2. Now, there are various things that we need to look at to record when we have a look at these graphs. And the first is the period. And the way in which we're going to do that is get the time taken for 10 oscillations and divide that time by 10. In order to get a more accurate result, I'm going to click on this one here, the displacement. I will just right click here to make sure it is at the front, and then I'll extend this down and spread the graph so I can get a more accurate reading of the numbers involved. It just takes a bit of playing with. And I'll just try and get it so that the graph starts up here at the peak of this wave here. And I'll use the marker here to find its exact coordinate. So I'm moving that to the top there and moving this across here. Now I'm going to pick out 10 waves. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and click this to get an accurate reading. Now I've got to find this point here and bring that up and set it on the 10. So there we are. So there's the time for 10, for the 10th. There's the time for the first. And so you can see two figures there, 8.54, 1.80. So if we subtract those two figures, the time that we get is 7.42. And what that means is that the time for 1 is 0.74. So that needs to go into the table here, 0.74. While we've got that particular graph on display, what we can also do is find the maximum velocity of the 50-gram mass, its maximum amplitude. So what I'm going to do to get the amplitude is to measure the lowest point and the highest point. That's the distance they are away from the sensor, and divide that distance by 2. So this distance here is 0.31, say 65, and the one at the top is 0.34, and I'm going to say 0.34024. And what I've got to do now is get the difference between those two, which is 0.0761, and divide that distance by 2. And that will give me the amplitude. So that is 0.038. And I'm going to say 0. So 0.38. 0.038. Now we need to find the maximum velocity. What I need to do is to minimize this, maximize this, perhaps bring it to the front first. So I'm going to right click on the bar there. I'm going to right click on the top part here and click bring it to the front. And now I'll pull it up here, pull it down there, and pull the whole graph down and stretch this up. So what I've got down here is 0, and up here I've got, let's say, 0.102, 000, and the 1.280. And when I do that subtraction, so here you can see the two readings I need to get the time for the period, and it's 11.36 minus 1.28. When I do that subtraction, I get 10.18. Divide that by 10, I get a figure of 1.018 for the period. So we put that in the table. Now the next numbers we need are the two numbers which are going to give us the amplitude, and the top number up here is 0.23, And down here, we've got a figure of 1.98. So when we get the difference between these two numbers, we get a number of 0.032. When we halve that to get the amplitude, that gives us a figure of 0.016. So we put that in the table. Now we've got to get the velocity. So here's the stretched out velocity graph. And if I go up here, I can have a look at this and notice that it's 0.10, maybe 3. So we'll record that in the table for the maximum velocity. So there's the figure for the maximum velocity of the 100 grams. Now, of course, it's the 150. So here we've got the stretched out version of the displacement graph. And if we have a look for the time for 10 periods or 10 cycles, it's the difference between 12.14 and 0.02. So doing that subtraction, we get a time of 12.12. Dividing that by 10, we get a figure of 1.212. And we put that in the table. So there it is in the table. Our next task is to get the amplitude and the velocity. If we have a look at the value up here, it's 0.200, and the lower position of the mass as it vibrated was around about, well, what will we say here? 0.61, let's say. So if we get the difference between those two numbers, it comes out as 0.039. But then we divide that by 2 to get the amplitude, and that will give us a figure of 0.0195. And we put that in the table. So there's our figure of 0.0195. Our next task is to get maximum velocity. So again, here we've got a stretched out version of the graphs. And if I go up here and have a look at that particular value, I could suggest it's 0.10, perhaps 4. So we'll put that in our table. So there's our figure of 0.104. Next is 200 grams. So here again, I've done a stretched out version of the displacement graph, and you can see there for the time for 10 is the difference between 15.28 and 0.02. Getting the difference between those is 15.26. Divide that by 10 and we get 1.526. So 1.526 goes into the table. So 1.526 is the period for 200 grams. Now, the maximum amplitude. Again, looking at the highest position here, highest displacement is 0.242, and the lowest position here is, well, I'm going to say 0.202 or 202. So subtracting those two numbers, we get 0.40. Halving that to get the amplitude would be 0.02. Again, that goes into our table for the amplitude. So there it is, 0.02 for maximum amplitude, and now we go for the maximum velocity. So now having this stretched out graph for the velocity and having a look up here, we can see that perhaps our best number for this is 0.09 meters per second. So putting that in our table. So there it is, 0.09. I could add a 0 there for the maximum velocity for the 200 gram. Now next is 250, and we go for its period. So here again, we've got our two values that we need to get the time for 10. So this first figure here is 15.48. And the starting period or time is 0.02. So getting the difference between that gives those two numbers, gives us a figure of 15.46. Dividing that number by 10 gives us a number of 1.546. So putting that into the table, and there it is. 1.546, and now getting the value for the maximum amplitude, getting a reading for the top up here, 0.244 is that one, and 0.45 might go for 5 there, and down here might go for 2.113. So getting the difference between those two numbers and dividing by 2 would give me a number of 0.032, and dividing that number by 2 would give me a number of 0.016. So that's the amplitude. So again, going back to the table, so that's it there, 0.016. Now getting the maximum velocity. Again, looking up here across, and we can see that it's 0.065. So putting that into the table. So there it is there, 0.065. So with this data now in place, what we can do is copy it into a spreadsheet and do some of the processing that we need to do. So here we go. So here's the data here, and we've got the average value for K worked out there, and here's the data for the period. Now we want to have a look at the second aim of this exercise, and that was to compare the direct measurement of the period to that calculated from the mass and the spring constant. So in order to do that, which is this data here, let's just go back to the formula that we had here. That is that T was equal to 2 pi root m over k. So this was the third aim that we had, to compare the period as it was measured with the period calculated using this particular formula. That is that T is equal to 2 pi root m, the mass, divided by the spring constant. So let's go back to our spreadsheet, and here are those values here. If I click on this, you can see the formula that I've got up here that I've copied down into the rest of the column. And now we're in a position to actually do that. We can compare these two values here. So this one here, 0.74, 0.71. 1.3, 0.98. So those two are very close. These are very close. Those two are exactly the same. And those two are close. So I'll keep that in our memory bank for the moment till we see the point of this. Now, the next thing that we've got to have a look at is the graphs. the two graphs that we're being asked to draw. And the first is to see what relationship there is between the mass and the period. So in order to do that, we can create this graph of period versus the mass. I've got mass here and I've got period here. Basically, just to work out whether or not we're going to get a straight line. Well, look, that doesn't look like a straight line. So our next suggestion then is to, if we have a look at the instructions, to graph or to try and create a graph that is linear. What I've done in order to do that is, in fact, created t squared over here and graphed t squared against m, or m against t squared. So if I move the graph over here, the spreadsheet over here, we do get a straight line if we square the period. And then we can create a gradient and have a look and see what that gradient means. To see what that gradient means, we go back to the formula. T is equal to 2 pi root m over k. Now, if I square both sides, I get t squared being equal to 4 pi squared m over k. Now, what that then means is that k is equal to, forgot the squared, k is equal to 4 pi squared m over t squared. So going back now to the graph, the gradient of this graph is t squared over m. In other words, the reciprocal of what we were just looking at. So if I get the reciprocal of that, of this gradient here, and multiply that by 4 pi squared, that should give me the value for k. And I've done that over here. You can see the formula that I've used there. So this is a value for k, and I can compare this with the value for k from Hooke's law. And you can see that those two are very, very similar. Now, let's go back to the optional section, and that optional section related to looking at the maximum velocity, the amplitude, and this section here, which I haven't spoken about. This is omega. And of course, omega we think of as being an expression for the angular velocity. Now, we have mentioned that there is a connection between circular motion and simple harmonic motion. And this mass here that we've been looking at is simple harmonic motion. If we use the equation that V is equal to minus A omega sine phi, or if we use the equation that V is equal to A omega cos phi, we can say in a situation where the velocity is a maximum that this, well, cos phi here will amount to 1. So we get the equation that V, the velocity, is equal to the amplitude times omega. Now, omega then is equal to the velocity divided by the amplitude. So this is the equation. This is the column here that we have of these figures. Now, from that, we can use the equation that t, the period, is equal to 2 pi on omega. So once we've got omega, we can then divide omega into 2 pi to get another value for the period. This is what we've got here. So we've got 3 ways now of getting the period. We've got this one here, we've got this one here, and we've got this one. Now, in each case, we can make a comparison, and by and large, they are the same. What's the point of the exercise? Well, the point of the exercise is to show that there are different ways of finding out the things that we happen to be interested in here. And the 2 things that we're interested in are the period and the spring constant. So we can find out the spring constant through Hooke's law, and we can find out the spring constant by studying the movement up and down of the spring and looking at the period and the mass. And then we can find out the period these 3 ways. First of all, by measuring it. Secondly, by using the equation. And thirdly, by using another equation. And this process of verifying the data that we get and establishing something as being true and consistent by discovering it in 2 or more different ways, that shows that the process is a valid process. And this process is used in a number of different circumstances in science.